Hey guys, welcome back to Mind Mentor. This is the second video in the series of Discrete Mathematics. Again, the objective of this series is to teach you a introductory level, university level discrete math course. So in this video, we're going to cover logical operators and truth tables. So yeah, let's get into it. Let's start off with a few definitions. A proof is a sequence of arguments that lead to a conclusion. And the conclusion is gonna be a statement that proves the premise either true or false, right? So if I, said oranges are round, and I wanted to write out a formal proof for the case that oranges are round, then I would have to write out a sequence of arguments and then write a conclusion, which states that yes, indeed, oranges are round, or no, oranges are not round. And it has to be supported by the arguments that are used in the proof. Up next, a statement / claim is a sentence that must be objectively true or false, right? So, for example, 1 + 1 = 2. That's a sentence that is either objectively true or false, right? It's objectively true, obviously. Something like 1 + 1 = 7 is, again, a sentence that is objectively false, so that's also a statement. Something like, this is a nice computer. That's not a statement because that's subjective. Some people may say, no, it's not, and some people may say, yes, it is, right? So up next, a theorem is basically a statement that is proven to be true. So, for example, 1 + 1 = 2, that's a statement, but if we write out a formal proof of it, and we conclude that 1 + 1 is indeed 2, then 1 + 1 = 2 now becomes a theorem. And then we have a proposition, which is a sentence that declares a fact. And it's usually unproven, obviously until we prove it. An example of this could be, P of x, right? Where P means x lives in Paris. Right. So x is what we call the argument, or some people may call it predicate, right? So basically, what it is it's an input that we give into this proposition. Proposition in a mathematical sense is sort of like a function. So again, this is something that is true or false objectively. So for example, if x lives in Paris, then this is a statement that is objectively true. If x does not live in Paris, it's a statement that is objectively false. Next up, we have a compound proposition, which is a proposition modified with a logical operator. Also, something important to note that not all propositions, for the sake of this course, require to have an argument inside of it. So for example, on its own, y could be a proposition. So if we say y means I'm happy, that could be a proposition. It requires no input, and it could be objectively true or false, right? I'm happy is a little bit arbitrary. If you want to go really basic, we could say 1 + 1 = 2 is a proposition. And then of course we have logical operators. Logical operators are sort of like mathematical operators, but they're used to combine propositions and to make truth tables. So the 6 types of logical operators that we cover in this course are the negation, and this is the symbol for negation, right? And then we have the conjunction, the disjunction, the exclusive or, the conditional, and the biconditional, which is the double-headed arrow. And these are pretty straightforward. You should already be familiar with these, but if not, it's fine. We can go over an example. So, if we have a proposition X, and X means oranges are round, we can use this proposition, the negation. The negation means not, right? So if we write not X, that means oranges are not round, right? We could also have a conjunction, so it says oranges are round, and then we have another proposition that says oranges are orange. So then we could, combine it together in a conjunction, X and Y, which means oranges are round, oranges are round, and oranges are orange. Right, so yeah, basically this means not, this means and, this means or, this means exclusive or, but exclusive or as in it can be only one or the other. So in English we could write either or, right? So either A or B, either X or Y has to be true, but not both, right? And then we have our conditional, which is if then, and our biconditional, which is if and only if, right? And then how do we represent these? Well, we can look it up here in this. This is something we call a truth table. So we have our values X and Y here, and then we have, a series of true or false values for these propositions. We have X is true in this row, X is true in this row, X is false in this row, and X is false in this row. Oh, sorry, one thing that we forgot to mention is 1 is basically a statement that represents true in this course. And 0 is a statement that represents false, right? So when we write 1 true/1 here, that means X is true, and when we write F/0, it means it's false. So and then again, Y in this row is true, it's false in this row, it's true in this row, and then false in this row. So in this row, we have a case where X is true and Y is true. We have a case in this row where X is true and Y is false, where X is false and Y is true in this row, and in this row, they're both false. Okay, so now this is the truth table. So, when we combine these propositions using logical operators into compound propositions, what happens to the truth falsity of the scenario? So in this case, of course, we've got true and true. If element A is true and element B is true, or element X is true and element Y is true, then the entire sentence is true, right? If element, in this row, if element X is true but element Y is false, then true and false leads to false, and the same with the other way around, and then false and false also leads to false, right? And then you could use that to prove all of these values. So this is basically like a legend. It shows you, what the true falsity of the compound proposition is equal to. Okay, so now let's go over, a question that maybe you might find in an assignment, right, or an exam. They might give you a truth table. So we've got X and Y here, and we've got our values for X, true, true, false, false, and for Y, true, false, true, false. And then maybe we have a compound proposition here, X and Y. If X and Y, then not Y or X. Alright, so then it might ask you, well, evaluate the truth table using this compound proposition. So that's pretty straightforward. You just have to plug in these values for every row. So in this row, in row 1, you're going to have to plug in the value true for X and true for Y. In row 2, it's true for X and false for Y, and etc., and so on and so forth. So for row 1, we can plug in those values already. So it's true and true, If true and true, then not true or false. And then if we simplify it further, true and true evaluates to true. And if you have a hard time memorizing that, just look it up in the truth table right here. True and true evaluates to true. In this cell you can see, right? And then true or false, again, if you're struggling to find it, true or false is this row in this column. So it's this cell right here that also evaluates to true. So we have if true, then not true. So again, if we evaluate this down further, that becomes if true, then false, right? And if we take that, that's the second row in our truth table, and then the conditional one, so that evaluates to false, right? So then, for this case, the entire proposition boils down to false, right? So when x and y are both true. And then it's pretty self-explanatory. You can do the rest on your own. One thing that is important to mention is an order of operations, because order of operations is important in discrete mathematics and logical proofs. So the order of operations goes obviously parentheses first. So you can see that right here. We evaluated everything in the parentheses first. And then we have negations, conjunctions, disjunctions, exclusive or, conditional, and biconditional. Right? There's more logical operators than this. We've got, nor and a bunch of other ones. But these are the only ones we're concerned for the sake of this course. And this is the order of precedence. Precedence / order of operations. Right, so we evaluate what's in the parentheses first, and then we evaluate the negation of it, and then we evaluate the disjunction, etc., etc. So you can see over here that there's no parentheses around the negation, right? So once we got to this step, it was basically true, if true, then not true. So what do we do here? I drew a parentheses around it like this, but it wasn't there to begin with. So in a case where parentheses like that don't exist, we would obviously evaluate the negation first, because that's our order of operations. And then the conditional we would evaluate at the very end, right? So, this is something you should memorize. It's a pretty basic order of operations. And then lastly, let's move on to one last example, which is again something you might see in an assignment or an exam. So let's move this off to the side for now. Right, and then right here we'll add another row. So something else you might see in an exam is a function f of 5 or f of 1 or something like that, just f, right? And then it'll evaluate the question, it'll evaluate the function for you, right? So maybe f of 1 might evaluate to true, true, false, true. And then the question will ask you, define f of 1. So what is f of 1, right? This might look a little bit challenging to do, but it's really not that difficult. We use a method called disjunctive normal form. If you're in a logic course, you're going to dive into a lot more methods as to why something like this we could prove something like this true. But for the sake of this course, the method of disjunctive normal form will suffice. So using this method, step 1 of this method is to Step 1 of this method is to find all the instances where f evaluates to true. And step 2 is just separate them with disjunctions. And you're done. So how do we see this in practice? Well, we can see that f of 1 evaluates to true in rows 1, 2, and 4. Right? Now in row 1, if we have, x and then a operator and then y, that operator is usually going to be and, right? So if we have x and y, for simplicity we can keep it as and. If we have x and y and in row 1 both x and y are true, then f of 1 will evaluate to true, right? And then in row 2, we have something like x and not y, because y is false in row 2, you can see, right here. Y is false in row 2, so we have x and not y. So if we, substitute t for x and false for, not y, then we can get, false for y, then not y will evaluate to t, and t is just t. So true and true will also evaluate to true, right? In row 4, we've got not x and not y, since both are false. And yeah, so in row 1, this evaluates to true, this evaluates to true. In row 2, that evaluates to true, and row 4, that evaluates to true. So now we can just separate them with disjunctions, and there we go. We've solved the problem. This is the definition of f of 1. This is what f of 1 equals, right? Why is this? Because in row 1, this thing is satisfied. It doesn't matter what happens in the future, because this is all separated with disjunctions. It's all or. So, if we have x or y or z, as long as x or y or z are true, one of them are true, right? So as long as y is true, or as long as x is true, as long as z is true, then the entire thing is true. We don't even have to look further. So as long as this element is true for row 1, the entire thing is true. For row 2, this element is true, so everything is true. And for row 3, this element is true, so everything is true. In row 4, this element is true, and everything is true. In row 3, nothing is true, because, in row 3, we've got x is false and y is true. There is no bracket in the series which evaluates those two substitutions to true, meaning in row 3, the entire function will evaluate to false. So there you go. That's basically the end of this video. Introduction to logical operators and truth tables. Stay tuned for the next video, and if you found this helpful, please remember to like and subscribe. It really means a lot to us. Thank you so much.